We're going to look at definite integrals today. And what we've been doing is looking at indefinite integrals, which are just basically an antiderivative. It's a family of equations. Because of the plus c, it could be a infinite number of different equations for the antiderivative. Okay. A definite integral tells us the area under the curve from one x value to another, the area under the curve. Okay, so the definite integral is, if the function is continuous on the closed interval a to b, then the area of the bounded region by the graph of f is, and the x-axis, so like the area from the graph to the x-axis is defined by our integral. A is the lower bound, b is the upper bound, and f is the function. So if I have the function, let's say that f of x is equal to x squared, and I want to find the area, if I was to find the integral from 0 to 1 of x squared dx, I would be looking at, let's see, x squared is 1. What I would be getting is from 0 to 1 and the x-axis, what is the total accumulation of y values underneath the curve? So the area underneath the curve. So this gives us the area from x equals 0 to x equals 1. All right, so basically the value of a is always the leftmost or the smallest value in the interval. So if we're looking at the bound from 3 to 7, then our a would be 3 and our b would be 7. So we write the a on the bottom and the 7 on the top of the integral. And then what we get is that the definite integral is the accumulation of area. Like I said, the area underneath the curve. This means that the area adds to its value as it moves from, this is really important, from left to right. So we're adding the area underneath 0, then to the right of 0, and so on and so forth until we get our total area underneath our curve. Okay? If the value of b is smaller than the value of a, so the b value is smaller than the a value, what we do is we're allowed to switch the bounds so that the b goes to the top and the a goes to the bottom, but then I have to make the area negative. So for example, if I do 4 to 1 of f of x, I can rewrite that as the area from 1 to 4 of negative x. Or sorry, the area from 1 to 4, but it's negative, it's opposite. The area above the x-axis is considered positive. The area below the x-axis is considered negative. And this means that the area while moving right to left would be counted. So a negative area counted right to left would actually be positive. Okay. Oh, I missed some lines up there. Okay, so that would be like this. If this was A to B, if I was moving from B to A, the area is negative, but since I'm moving backwards, it's going to be considered positive. Okay, so looking back up here, if the value of b is smaller than the value of a, then the area is moving right to left, so it's backwards, right to left, or backwards, and will be considered negative. All right, so we're going to do some examples from a graph. So we have the graph of f prime, and I want to find the area under f prime. That's what the integral says, the area under f, under the function. So from 0 to 1. So I look at my bounds from 0 to 1. The area underneath the curve, it says is 2. So I'm just going to write 2. All right, so from 0 this time to 4. So from 0 to 1, 2, 3, 4, okay? It's an accumulation of area, so I'm going to accumulate the area from 0 to 1, and then from 1 to 4. We would write it like this, from 0 to 1 of f prime of x dx plus 1 to 4 of f prime of x dx. And the area of f from 0 to 1 of f prime of x is 2, and the area from 1 to 4 is 6. So 2 plus 6 is equal to 8 units. I can see that both of the curves are above the x-axis, so the areas are both going to be positive. Okay. All right. Next up, from 1 to 6. So this time we need to add on. Ooh, from 1 to 6. Okay, just kidding. So from 1, x equals 1 to x equals 6. We're literally just going to add the areas. So we're adding 6 and then the area of 3, but the area of 3 is below the curve, so it's going to be 6 minus 3, giving us 3. All right, next one. We have the area from 4 to 8. So from 4 to 8, moving right to left to right is from, let's break this up, from 4 to 6 of f prime of x dx. The area is -3. And then we're going to add on the area from under the curve from 6 to 8. So the integral from 6 to 8 of f prime of x dx. And that area, it says, is 7. So we're going to add 7, giving us a total area of 4. All right, so from 0 to 8, we're just going to add up all the areas. I have an area of 2 plus the area of 6 minus 3, because it's under the curve, plus 7. And that is going to give us 12. Okay, and our last one from 4 to 1. So this time we're moving from 4 backwards to 1. And so we can rewrite this as 1 to 4, but we have to make the area negative of f prime of x dx. So I'm just going to look, what is the integral of f prime of x from 1 to 4? The integral from 1 to 4 is the area under the curve, which is 6. So the area is 6, but then I need to bring down the negative. So moving backwards, the area would be actually -6. All right, next part. So some properties of definite integrals are, if f is defined at x is equal to a, then if we have the integral from a to a of f of x dx, then the area under the curve would be 0. So an example would be like the integral from 1 to 1 of f of x dx. Well, we didn't move anywhere, so we didn't accumulate any area, 0. Okay. We saw in our last example that if c is between the interval a and b, we can split up the integral into pieces. So I'm going to split up from a to b of f of x. The integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral of b f of. So an example would be like, if I know that we're evaluating the area under 1 to 7, I have a value c is in between 1 and 7, so I can integrate from 1 to 2 plus from 2 to 7, so we can split it up, just like we did on our graph last example. So number 3, if I have the integral from a to b of k, which is a constant, times f of x dx, we can move the constant out to the front of the integral, or out of the integral, and just evaluate the function f of x dx on the interval a to b. Okay. If I have two functions being added together, like terms of polynomials, for example, we could evaluate this as the integral from a to b of f of x dx plus the integral of a to b, again, same bounds, of g of x dx. Okay, so an example would be like the integral from 0 to 2 of x squared plus 3x dx. I could split this up as from 0 to 2 of x squared dx plus from 0 to 2 of 3x dx, if I wanted. All right, so if we have an even function, then remember an even function has symmetry, a reflective symmetry across the y-axis. So if I evaluate from negative a to a, then what I have is two copies of itself. So I can evaluate an integral from 0 to a of f of x dx, but then I know it's a double copy of itself, so I'm just going to multiply it by 2. So the area will be the right side times 2. An even function and an odd function. An odd function has symmetry across about the origin. So if I have the value negative a and a, then the right side's accumulation of area will be canceled with the left side's accumulation of area. So I just get 0. That's kind of fun. All right, let's do a few examples and then we'll be done for today. Okay, so we have the integral from 2 to 4 of f of x dx is equal to 5. The integral of from 2 to 6 of f of x dx is equal to negative 6. And we want to find the integral from 4 to 6 of f of x dx. So I see that I just want a portion of a much larger piece. So I know that the integral from 2 to 6 of f of x dx, so the area under the curve from 2 to 6 is equal to the area under the curve from 2 to 4 plus the area from 4 to 6. And then I can start evaluating. So from 2 to 6, the integral is negative 6. The integral from 2 to 4 would be 5 because it's given. And then I need to add, I don't know, the integral from 4 to 6 of f of x dx. So we're just going to isolate this guy by subtracting 5. So I get negative 11 is equal to the integral of from 4 to 6 of f of x dx. And that's my answer. All right, one more. I have the integral from 1 to 3 of x squared is equal to 26 over 3. From 1 to 3 of x dx is equal to 4. And from 1 to 3 of just dx is equal to 2. Basically, there's an invisible 1 right here. Okay. So we're going to evaluate this polynomial here. So I have the integral from 1 to 3 of negative x squared plus 4x minus 3 dx. And I remember my integral property rules, and I remember that this is equal to all of my terms split. So I have 1 from 1 to 3 of negative x squared dx. So I'm going to split each term into its own integral, plus from 1 to 3 of 4x dx. And we can only do this with terms, not with factors, okay? Terms. So polynomials we can split apart. Or pieces that we're adding together, even if they're not polynomials, okay? All right, so using my my integral properties again, I'm gonna take out this negative. So I get negative on the outside because it's a constant, so I can bring it out to the front. That's my k value. So I get x squared dx plus, again, I'm going to bring the 4 out because it's a constant, from 1 to 3x dx minus 3, because it is a constant, from 1 to 3 of dx, or 1 dx. All right, Then I remember that 1 to 3 of x squared dx is 26 over 3, but I'm going to bring down the negative. The integral from 1 to 3 of x dx is 4, so I'm going to add 4 times 4, minus 3 times the integral from 1 to 3 of dx, or 1 dx, is 2. And then I just simplify, giving me 4/3. Okay, and that's it for today. If I could stop this